English, or be it anything else that I am going to show to you, feel free to type anything into the chat, preferably in English. But of course, you can also do it in Latvian. And we are very lucky that Yanis is still with us in this session. He will not translate everything I will say, but in case it's needed, he can maybe help me sort it out, or someone else can sort it out. But I think we can use the chat. I think it makes it a little bit easier. And I will hopefully, I'm monitoring the chat, so I hope I don't oversee anything or overlook anything if I continue talking. So welcome. I'm really happy to have so many people in this breakout room. To be honest, when I heard the word workshop, I was of course thinking of, you know, a little bit more interactive setting than doing it remotely. So I would love to be now with you in Latvia, but I'm afraid that we will not be able to see each other, at least for the next couple of months. So we will do it in this way. The idea is I prepared a lot of material. So what I want to do during this next 50 minutes or so is I want to show you a lot of things that me and my team, my PhD students, have been actively working on in the past couple of years. So we are at CERN, we are a team of PhDs and postdocs and myself. We are working on how to get particle physics or elementary particle physics into the classroom. So how can we support you as teachers with material? So for example, experimental setups that you can really use in your classroom, but of course also some material in terms of what kind of problems students may have when we talk about particles, for example, or what kind of strategies might be useful. What I want to say at the very beginning, this whole workshop, what I'm doing is not, I'm not going to tell you this is how you have to teach, by no means. That would not work. You are all the experts and you are all the teachers. You yourself have your own way of how to teach. All I want to do is I want to give you some ideas, some of which you might find interesting and you want to find them, try them out. Some of them you might not find interesting or they are not applicable to your daily teaching. That's perfectly fine as well. So I hope that what I prepared will be interesting to everyone. So let's see how it goes. Maybe before we really dive into, I want to introduce myself. And so with my slides, I want to show that before I worked at CERN, I was a teacher myself. So I started as a physics teacher myself. And on my slides, you can see, well, it doesn't look like a school, but that was the school that I was a teacher at. It's in Vienna, in Austria, where I'm from. I'm from Austria. And this school is called the school ship. And it's really that. These are two ships, two old ships, which are permanently attached in the Danube River. So you see, this is in Vienna, in the Danube. And in there, we have a standard high school, completely open and a high school, but a little bit of a special high school. So that's where I was a teacher for a couple of years. I taught physics there. It's a fantastic school. Whenever you have to teach anything with fluid dynamics or anything with fluids, you have no problem because the water is just outside of your window. So you have to experiment outside there. So it's a fantastic school. So that's where I started teaching myself. And then after a couple of years, I left Vienna, I left the school because I wanted to do something else. And then I ended up in Cambodia in Southeast Asia, where I then was a teacher in an orphanage. So you can see me there with all those fantastic kids around me. I was one of the best times of my life and I learned a lot. You learn a lot when you teach in those very, very tough environments. And then I was very fortunate that from Asia, I made it to CERN, where I did my PhD, then a postdoc, and by now I'm, as I said, one of the few staff scientists. So I'm a very, very lucky person. I'm really fortunate and I'm very happy with my life so far. And the picture that I show you here is exactly what I do if there is not a pandemic. So unfortunately at the moment, this is not what I do, but before Corona, I had one group of teachers from different countries who come to CERN and we prepare a program for them that lasts a couple of days. to have lectures, visits, and workshops. And at the end of this workshop, I will highlight those programs again, because obviously they will continue, not necessarily now and not necessarily live, but in a couple of months or years from now, everything hopefully will be back to normal. And then I hope that some of you or all of you will have a chance to at some point come and visit us at CERN, so we can show you how awesome this place is. Okay, so yeah, and as I pointed out, I'm by now a professional group picture taker, so that's what I do on a daily basis. These days I do group pictures like this, so we take screenshots of Zoom calls, but usually I am someone who stands with a lot of teachers, and I'm really, I have the best job at CERN, this is for sure. Part of my PhD when I was working at CERN was that I did a PhD thesis entitled Elementary Particle Physics in Early Physics Education. So exactly the title that I gave this workshop. And so my research was really on how we can introduce elementary particles to young students, let's say 12-year-olds. The reason for that is with 12-year-olds, whatever I did it with students who had no physics education. So what worked, I could take. What didn't work, I had to change. And I'm not telling you in any way that you now have to go to your students and teach them particle physics from the early age. Absolutely not. But all the results that I have and that now my PhD students are also replicating, they can be helpful for you when you want to introduce particle physics at any age group. So that is the motivation. Okay, so that was already a lot from my side, and I talked a lot and maybe a little bit too fast in English, so I will slow it down a little bit, and I will start with the toughest question at CERN. If it's the one question we are most afraid of, and the question is, what is a particle? This is a tough question. And so if you want, I invite you, you can use the chat. And if you want, you can type in what you think a particle is, just so we see what some people in the room think a particle is. If you want, you don't have to, but let's try that out. If some of you have an idea what a particle is, I would be very interested and curious to see what you think. We should have a chat in the breakout room. Yes, yes. So. But you don't have to, so don't feel forced. Okay, yeah, it's something we can't see. That is for sure. That is a very good answer. Okay, it's a little part of something, a particle. Absolutely, I like it. Yes. The smallest thing. Okay, nice. You can also type it in Latvian, of course. I'm pretty sure someone can translate that for us as well if you don't want to spell it in English. It's a small amount of matter that builds something bigger. Absolutely, I like it. A primitive Lego brick. Okay, awesome. Yes, small and undividable or indivisible. Absolutely. Beginning of something, mass and energy. Lego brick. Okay, yeah, for everything. I love it. Awesome. Okay, very nice. Wow, that was a nice collection already. Thank you so much for everyone who typed something into the chat. So you see, the common theme is something that we can all agree on. Apparently, it's something small, and that is perfectly fine. But the problem is, and that's the reason why I start with this question at the beginning, there is no definition. We don't know what a particle is. So don't get me wrong. Of course, we have fantastic models. We have different ideas. So in quantum field theory, we consider a particle to be the excitation of a quantum field. So that is one idea that we have. But then, of course, there are other models that describe particles, for example, as the smallest building blocks. So depending on which side of science you look at, you get different definitions. There is not one that is universally agreed upon because we don't know. And I'm pretty sure that in this room, there are not just physics teachers, there are for sure also science or chemistry teachers. So we all know that depending on what we teach, we say particle, but we mean completely different things. So in particle physics, we might mean the elementary particles, like an electron, for example, that is a particle. But in physics, when we teach, for example, the ideal gas scenario, so we have this box with the atoms inside, and if you increase the pressure, if you increase the temperature, the pressure increases, and then usually we have particles inside of this box. But in this case, the particles represent atoms. And in chemistry, molecules can also be represented as particles. So you see what I mean? There are different things that can be described as particles. And this is perfectly fine. This is how science works. We have different models. But for our students, that is a huge problem, because they are not informed like us. We have studied that. We know what we are talking about. But for students who need to figure out everything, they get confused super easily if the one teacher says, this is a particle, and then in the next class with the next teacher, they use the word particle for something else. So this is something where it all started, where we have confusion with students if we as teachers are not careful what we say in our classroom. So let me just go back to my presentation. Okay, so we know from research already that our students are influenced by different things they encounter that can cause misconceptions. So conceptions that are not scientifically completely accurate. And here, for example, we have everyday experiences. I mean, our students, like us, they go through the world. And if we want to teach them particle physics, they don't see particles in their everyday life. They don't see that, sitting in front of a computer, there are particles. They don't see that. It's not part of our daily experience. And so that, of course, influences their experience. In particle physics, we have some inadequate learning offers. So we have some animations or simulations that are nicely designed, but they are just completely wrong. And for us as teachers, that is quite easy to discern, to say, okay, this is not correct, this is okay. But for our students, they don't know what is correct and what not. So we have to be very careful when we use them. So yeah, the illustrations and animations. So what are some documented misconceptions in particle physics? Well, as I said, our life does not look like there are particles. That is not something our students grow up with. They see the table, the computer as solid objects, so a continuum and not a discontinuum. So they don't necessarily see that all of matter is made of particles. They don't see that. If we as teachers tell them that there are particles, they try to make sense of it and then they overlap it. So what they do is they say, yeah, no problem. I am made of matter and my teacher tells me matter is made of particles. Well, no problem. Then the particles are inside of my hand, for example, but they don't necessarily accept that the hand is made of particles. They just say, yeah, the particles are inside. And that is not a correct, or the full correct description. If we as teachers talk about particles in the classroom, that is difficult for students. So what they do is they make it easier for them. So they transfer macroscopic properties from our life into the microcosm, so to speak. That is really something that we found in our research. When teachers introduce particles in the classroom, for example, the proton or the electron, then students tend to think of the proton as a very, very heavy person because it has a lot of mass, but it's positively charged. So the proton is a happy, fat person, so to speak. And in opposite, the electron with a tiny mass and it's negative, students think of the electron as a mean, tiny thingy. It's really true. I'm not kidding. This is what students try to make sense of. And I'm not against that, but we as teachers should know that this can happen so that we are prepared to address those misconceptions. And last but not least, one thing when we talk about atoms, for example, one thing that students are really struggling with, and I think it's the same for us as well, the fact that those particles that make up atoms are always in movement somehow, that is very difficult for students to understand. And the notion of empty space, so that there is nothing except for particles, is also very, very difficult for students. So this is what the literature tells us. I just wanted to briefly summarize that for you. And now I want to show you what we have come up with. So suggestions, how we can address particle physics in the classroom. So what kind of strategies can work? Again, I'm not saying that this is how you have to teach them, but I want to present them to you and you can then decide if that sounds interesting to you or not. So let's start with the so-called model aspect. So in science, in physics especially, whatever we do is based on scientific models. This is something that is quite natural to us. For our students, unfortunately, this is not something they easily accept. For them, they like to know the facts, because for them, physics or science is already quite difficult. So they want to study something and then they want to hold on to this knowledge. But we in science, we tend to say, well, this is a model, we describe something with it. But if that doesn't work, we have a different model and we can change things. And students don't like that because they have a hard time to learn something. And when you then tell them, well, but this model is not the best, we have this model, the students are like, but I like this model. I just spent a lot of time understanding that, so I don't want to learn something new. So that is something where students have struggled with. And in particle physics, this is something where we can always emphasize this aspect, that we can always say, we don't know what a particle is. I mean, as we just discussed, it's something small, but what it really is, we have no idea. So it's always a model that we are talking about. And our research shows that the more often teachers showcase and emphasize that it is all a model, the more students tend to accept that. But it's really something that is very difficult for them. So in particle physics, we can't say anything else, but it's a model, so we should use that. The second thing is something that is completely known to you already. I'm 100% sure. I'm not going to tell you anything new there. I just want to emphasize that linguistic accuracy, so what we say in our classroom and how we say something in our classroom, is completely important. And I mean, as I said, this is not new to you. You all know that. We all know that. It's not just in particle physics. It's every time we teach, we as teachers have to think, what do I say and how do I say it? But in particle physics, it's not easy to be precise, because in particle physics, we use some terms that are really confusing to students. So let me show you what I mean. The term particle itself, I mentioned at the beginning, it's used in different areas, completely different. But in particle physics itself, it is also used in different ways. So for example, we call an electron a particle, but we also call the proton a particle. And that makes sense to some extent, but if you want to explain to students that a proton is made of quarks and gluons, then it gets more difficult, because for students, a particle is same as what you put in the chat. It's the smallest thing. It's the smallest building block. So a particle is an elementary particle. So if we call the proton a particle as well, that is difficult for students, because we can open it up, so to speak. We can see inside. And so here, a suggestion that we found very helpful is to call only elementary particles, like the electron or quarks, particles. But the proton is then a particle system made of particles. And this can still have particle-like properties, but for linguistic accuracy, this distinction can make a lot of sense to students. So I highly suggest that you think about it and maybe try it out, because that makes a lot of sense. And it goes very well with my third thing that I want to present on this slide. And it's the one thing I'm most proud of, if I may say so. So this is really something I like a lot, because as teachers, we have to represent something. We have to use images of something. We have to show our students what we talk about. In particle physics, this is very difficult, because no matter how we draw a particle on our blackboard or on the whiteboard, it's going to be wrong. We don't know how a particle looks like. So whatever we do, it will cause misconceptions. And some of them are okay. Some of them can be really problematic. So for example, if we draw an electron, an elementary particle, in like a circle or even like a small ball, like a sphere, that is problematic, because our students say that it cannot be elementary, because they know a ball, I can cut it open, I can take it apart. So that is an issue. So here, my clear suggestion is, in particle physics, to use what we already use in physics, in Feynman diagrams, for example. We use typographic illustrations. So it's a fancy name for saying we use the letters themselves. So you see here on my slides, I have a proton and a neutron. And these are particle systems that are made of the quarks. In this illustration, I omitted the gluons, but they can come later, of course. But here, very simple, we see the elementary particles, the up quarks and the down quarks, and they make up either the proton and the neutron. And so this is a very easy way for teachers to say, we don't know what a particle looks like, but of course we have to write it down somehow. So the electron is an E, the up quark is an U, and if we want to draw a proton, well, then we just take a P, or the neutron, the N. So it's a simple way of still showing that there is something tiny, because obviously each letter represents that, but we don't know what it looks like, so we don't even care, and tell that actively to our students. All right, so you can see I'm a little bit proud of that. I hope this is something that you find interesting. Try it out, and if it works, let me know. If it doesn't work, let me know, because either way, I need to know to see if we can either push it forward or if we have to adapt it. So far, the feedback from teachers is very positive. So we have tried it out with a lot of different teachers in different countries, and so it's one way of doing it. Now, I want to briefly stay on this illustration of proton and neutron, because during such a workshop, for me, it's very important to give you something that might be new to you, but it might be helpful. So I hope that this will be helpful for you, because you see on my slides, the proton is made of up quark, and a down quark, whereas the neutron is made of a down quark, and an up quark. I don't know if you have that in your head. I don't know if you have memorized that yourself. I, to be honest, found that super difficult to keep in my head. What is a proton made of? Is it down, down, up, or is it up, up, down? I could not really memorize that. I could, of course, look it up or calculate it, but I never really had an idea, until I introduced that to one of my students. When I was a teacher in high school, I had one of the smaller ones, the 12-year-olds, and I taught that. But I told them, I can't memorize it, so it will not be on the test. I was a nice teacher. But then the next day, this little student, a small student, Anna was her name, she came to me and she said, you know what? She was super excited. You know what? It's super easy to memorize that. And then she told me, and she blew my mind, and I will now tell you, and I promise you, you will never forget it. So she showed me, look at the proton, the proton. The proton has the symbol of a P. I said, yeah, okay, so the P. And she said, if we flip it around, the P becomes a D, so that you can memorize that the proton has one down quark and two up quarks. And I was like, Ah, yeah, that is smart. But then Anna was like, but it gets even better because the neutron is an N. If you flip that around, it is one up quark, one U. So we can memorize the proton, flip it around, one D, so one down quark. For the neutron, flip it around, one up quark. So the neutron is one up, two down, and the proton is two up, one down. I don't know if you liked it. I loved it a lot. And since then, I can't forget that at all. And I hope that is the same for you. Is it important to know what a proton is made of or a neutron is made of? No. I mean, that is not important knowledge. But if we can memorize it like this, why not? So maybe this is a way how we can, motivate our students as well. So I wanted to give you that, and I hope you like that. Okay. And I promise you, you can never forget it as of now. So there you go. Okay. So if you want to read about all of those ideas, how to introduce elementary particles, I wrote a paper where I summarize all those ideas and I give some examples, and all of my publications are available open access. And so you can, for example, download them via my website, cern.ch/jeff.wiener. You just Google my name and you will find my website anyway. And there you have all the papers that I ever published. Everything is in English. Some of them are in German as well, if you speak German. And you can read up more about that. So I don't want to go too much into detail here, but I will highlight a couple of more things throughout this session. So if it's okay for everyone, I would just move on to one thing that I fully understand is not, it's not really part of our curriculum. So usually, of course, I don't know your curriculum that much in detail, but usually what I will present next is not really covered at high school physics. But I want to use it as an example to show you how careful we as teachers have to be when we talk about particle physics. What I mean is, let's look at the proton one more time. So we have the proton here, and maybe at some point you want to discuss antimatter in your classroom. You might want to talk about antiparticles, because that is a topic that is absolutely relevant, and it's something that interests students a lot. So then you might want to talk about the antiproton. And now you see something within my the illustrations that I use. The proton is a particle system. So the P is just gray because it's not really a particle. But the quarks themselves, they are particles. They are elementary particles. So they have colors. And some of you might have already spotted that these colors are not just there by random. They prepare the so-called concept of color charge. I don't know how much you know about that, but it's the idea that every particle, like every quark, has a so-called color charge. And that's how we describe how three quarks can form, for example, a proton or a neutron. So, of course, this does not mean that the quarks have a color. It does not mean that at all. It's just our model, how we describe how three things can add up to something neutral. So that is a model that came from physicists in the year, I think 1964 was when the paper was published. So it's quite old. And they just thought, hey, wait a second, in physics, we know from optics that red light, blue light, and green light combined makes white light. So that is the concept of additive color mixing, which I'm sure we all know about anyway. But we use it here in particle physics as a model to explain how the quarks form particle systems. So it has nothing to do with the color mixing. It's just a representation. Our students do not know that, or at least they might know about color mixing, but they don't know that we take that as an example in particle physics. So this is really where it gets very confusing. So we have to be very careful there when we teach that to our students, because we know, but they don't. So we have to be very careful. But the moment we talk about antiparticles, like antiquarks, who have an anti-charge, that now gets really, really complicated. And I appreciate it's probably not part of your curriculum, but I just want to show you what I mean. Usually when you Google antimatter on Wikipedia, you can find a representation similar to what I have on my slide for the antiproton. So they use the complementary colors of red, blue, and green, which, to be honest, I have some troubles with, because I'm not colorblind, but I know some of our students can be colorblind. So for them, it might be difficult. And it's very difficult to memorize which color is the anti-color of which. That is a lot of effort that goes into it. So here we developed a different approach, which is very simple. So we tested it with students, and they confirmed the same problems that I have with color charge, because one student said, isn't the complementary color of blue orange, and of green red, and of yellow pink? So she asked that during an interview that we did with students. And at first, I did not know what that means, because it was a little bit, it sounds wrong. But then I interviewed a lot of teachers, and they confirmed something that you might know as well. Students, when they go through their high school years, they encounter different color models. So they don't only learn about colors in our physics education, they might also learn in arts and crafting about colors. And there they can use completely different color wheels, which is perfectly fine, but we as science teachers have to be prepared for that. So as I said, color is a difficult topic. So instead, we suggest to just use the same colors if you want to do that at all in your classroom, or if you have to do it, but instead of using different colors, use the same, and have a stripe pattern or any other thing, it doesn't matter what, to just show that it's anti-particles. So I know it's not super important in your daily teaching, but it shows again how careful we as teachers have to be, especially in topics that are very abstract, like particle physics. If you want to read about this alternative proposal, well, I published a paper here as well. So just in case you're interested, you can read about this paper. And where can you find it? Of course, on my website. All right. Yeah, I talked about the CERN and the accelerators we have at CERN a little bit during my talk earlier. But now I want to highlight for you as teachers how you can maybe introduce all these beautiful things we do at CERN in a nice way in your classroom. And I'm coming back to the point that I just made. You might not have time for that, or it might not be in your curriculum. At least that is my experience from talking to a lot of teachers from around the world. There are some countries where particle physics is not added in the curriculum, and there are some countries where particle physics is just added at the end. And that is difficult because it is a huge topic. So here, some colleagues and myself, we looked at this beautiful accelerator chain that we have here. It's so beautiful. And of course, there is a lot of physics going on in each of those different aspects. And what turns out is you can connect every single physics curriculum topic to any of those accelerators, because they all use classical physics. I mean, if we talk about acceleration of particles, we talk about electric fields. That is in the curriculum. If we talk about bending a particle beam around a circular track, we talk about this fantastic sign right here, which is called Lorentz force, or depending on from which country you are from or how you learn it, it's sometimes called right-hand rule, or in the UK system, it's one of Fleming's rules. So different names for the same thing. We need the right-hand rule to steer particles around the corner by the help of magnetic fields. And of course, circular motion is in there, thermodynamics with the cooling of our magnets. The vacuum pipe is also thermodynamics. So you see where I'm going with this. There are a lot of topics in our curriculum that can be linked to each one of CERN's accelerators, or any other accelerator. It doesn't have to be CERN. I'm just a little bit biased there. Apologies. So what we did is we wrote a paper, again, open access, and it's really written for teachers. This is really for you, and I hope that this is something that you might find interesting. We give you an easy description of how the accelerators and the LHC work. Of course, we are not combining all the accelerator physics in one paper, but it's an easy description in such a way that even students can read and understand it. But for every single chapter of this paper, we highlight the links to the physics curriculum, some of which are super easy for you, some of which might surprise you, because there are some things where you might not have thought, that's where particle physics comes in as well. And so if you read through this paper, you might get some ideas how to maybe sneak in some particle physics in your teaching if you want to. Or what I heard back from a couple of teachers, and I like this a lot, for example, in Austria, physics teachers are encouraged to, at the end of the high school education of their students, so when they are 18 and before they graduate from high school, they are encouraged to summarize the whole physics curriculum in a couple of weeks. And so here, a lot of teachers have used CERN as an example and said, we are now going to understand how CERN, one of the most advanced technological places in the world, works. And they show to the students that they don't need any new physics because everything they learned over the past couple of years is sufficient to explain everything in there. I really like this idea. So maybe this is something for you. Okay. Where can you find this paper? On my website. I'm sorry, it's a shameless advertisement, but it's just the easiest way to do it. All right. I'm almost done with showcasing what we did. So I hope that I will finish early so we can have some questions as well. I mentioned this coffee mug. It's really a coffee mug. If you ever come to CERN, you can buy it in our shop, and it has this beautiful formula on it. It's called the Lagrangian. It's the short, or the very, very short version of how we describe the standard model of particle physics in a Lagrangian way. It's not easy. I'm not kidding. This formula is not easy because it's already the very short, compactified version of a longer one that takes about 2 pages of formula. Very difficult. So we, a colleague of mine with another theoretical physicist, we sat down and we wrote a paper where we explain every single term, every single symbol you see in this formula. We explain what it means, what it does, and again, how it connects to the physics curriculum. I'm not saying that this replaces 5 years of studying physics and being a theoretical physicist, but at least with this paper, which is nicely called "Let's Have a Coffee with the Standard Model of Particle Physics," because after all, it is printed on a coffee mug. If you read that, you get an idea of what the standard model of particle physics actually describes. It is still a quite difficult paper, so the papers before, they are easy to read, super easy. This one is a little bit challenging, but I hope if you're interested, you give it a read and you might find some things that are really interesting in there. And at the end of this paper, there's a nice summary where we really explain what does that mean. And that, I think, can be used in the classroom. So check it out. Where can you find this paper? Well, on my website. Sorry. Okay. And okay, here, when we tested that, because it's not just us writing papers and just giving them to you, whatever we do, we always try out with students because we want to understand if what we think is correct works and also to get some feedback. And there is one feedback from students that I really found fascinating because we discussed what happens at CERN in collisions and when particles are created. And at some point we discussed with a student, he was 15 years old, and he mentioned, when we talked about particle decays, that he said decay is not the correct word, because he said that they transform into each other. And at first I didn't really understand what that means. But then I looked at the interview one more time, and what we did was we looked at the Feynman diagram. Yes, we did show them that. Of course, we did not calculate something, but this is the representation of what happens when a muon stops existing. So a muon has a short lifetime of 2.2 microseconds, and then it transforms into the muon neutrino. But that only works because there is a W boson involved, because it happens because of the weak interaction. And this W minus boson then itself transforms into an electron and an anti-electron neutrino. Usually in our textbooks, if at all, it only says that the muon decays into an electron and two neutrinos. That's usually what it says. But the word decay is not easy for students, because for students, decaying means that the muon breaks up into the other particles. Whereas the word transformation is the way better word to explain what happens in transformations of particles. So this is one suggestion that we at CERN now really use. You can also see it in our press releases. We usually use the word transformation because it just really describes this process better. And it again is just an example of linguistic accuracy that is really important. Okay. Now I really want to come to an end, and at the end I want to show you not just papers that we have written for you to read, but we also have a lot of material that you can use at home or in your classroom for free. So it's really something we at CERN in our beautiful laboratory. So you see here, this is School Lab, which is very important to me because I was at some point in charge of developing it. And in this lab, we have a lot of PhD students who develop very, very simple or sometimes very difficult, but still very cheap experimental setups, because we really want to make education as cheap as possible. This is really a very important part for us. They have a website as well. So if you want, you can check out their website. It's called cern.ch/schoollab, or you just Google School Lab CERN and you will find it. And what they have, I would just highlight two things. Since in my previous presentation, I showed you the Atlas detector, or at least the almost finished Atlas detector. And what you can see here is actually the coils that create a strong magnetic field inside of this detector. They are huge. And we had a student who designed this Atlas detector as a 3D model. Look at this beautiful thing. I'm not kidding. This is really something you can download from our website for free. And then you can either 3D print it if you have access to a 3D printer, or you just build it out of cardboard or whatever you want. But it really works. So if you take copper wire and you make a lot of coils out of them and you solder them together, and then you apply some 12 volts or so, you can really measure a magnetic field that is identical to the magnetic field that Atlas uses in the real world. And this is a fantastic example of how to make it a little bit more accessible to our students, because the picture on the left, it's a little bit difficult, but with this model on the right, it gets more attractive. And I can promise you, if you print that and build it, that even looks amazing in your living room. I promise you, it looks awesome just in your living room. Okay. And one more thing I want to highlight before I come to an end, because here you see a particle trap. Yes, you can 3D print a particle trap. You can also buy particle traps. You can really buy that online. It costs about 5,000 euros. It's incredibly expensive. Or you go to School Lab website and then you can download the files for free. You print it. You need some electric components. So the overall price tag is about 30 euros maybe. And then you have your own particle trap where you can trap dust spores or something. And you can see on the picture, this picture we took with a cell phone camera. So it's really, really beautifully visible. and completely for free, of course. You just have to download the files. And even if you don't have a 3D printer, by now there are online shops where you send files to, they print it for you for a little bit of money and send it to you via post. So there is no problem there. And that is just making education cheaper. So all of that and way more material. I just highlighted 2, there are by now 10 or so, you can all download via our website. And we hope you do, and we hope that will enrich your teaching once we go back to teaching in the classroom, of course. And then last but not least, as I mentioned, in my day job, I am in charge of CERN's teacher programs, which some of you already know because I recognize some of your names. So very happy to see some alumni from CERN already here. And for those who have not been to CERN, you can check out the website teachers.cern. At the moment, it's a little bit sad because all we do are remote programs, if at all, but hopefully by next year, we will start again, and then you might have a chance to come to CERN and stay here with us. Yes.
5 seconds.